Good afternoon, people. Good afternoon. Got it. People, what exactly are we doing? Well, there was probability since the class is happening after 3 days. So I guess we can have a quick recap. So in probability 1.1.0, we had three axioms. This was the beginning of building a great structure of whole probability course when we proposed three belief. We proposed three core truths. Can you prove these truths? No, you cannot prove these truths. These truths can be proven. These truths are just a common belief. Of course, they have not been disproven. Most of such things are like this only. For example, when you say the mass of the universe is conserved, it's a common belief. Nobody has actually measured the mass of whole universe. But there is no principle, there is no machine, there is no phenomenon that has been found violating this general principle of law of mass conservation. Similarly, when we say that the energy of the universe is conserved, nobody has actually measured the energy of universe. Forget measuring the energy of universe. Actually, nobody has measured the energy exactly. I'm not saying approximate estimations, but nobody has measured the energy exactly received by our planet Earth through various sources and dissipated by planet Earth in various mediums. So the idea is that there are certain common beliefs and we find no evidence against them. We say those beliefs are the universal truth. Axiom number one is that there can be no event ever whose probability is negative. Either an event will have some chance of taking place, or that event will have zero chances of taking place. In worst case, it will not take place at all. The second axiom says that the probability of whole sample space is going to be equal to 1. And the third axiom says that probability of union of two events, probability of union of two events is simply the sum of probability of first event and the second event. Probability of the first event and the second event, given that A and B, they are mutually exclusive events. Cool. In probability 1.0, then we entered into finite sample spaces with equally likely outcomes. Finite sample space like rolling a die with equally likely outcomes. with equally likely outcomes. In such cases, the probability of each outcome, whether you calculate the outcome of probability of element E1 or probability of element E2 or probability of element En, the probability of each outcome, each possible element of the sample space is 1 upon capital N, is 1 upon capital N. And if you define an event, if we define an event and that event has got, so let's define an event and that event has got some, let's say, n number of E1, E5, blah, 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 n number of outcomes, small n number of outcomes satisfying that event, small n number of outcomes satisfying that event, then from axiom number 3, I can write them simply PE1 plus PE2 plus PE3 plus PEN. And since each one of them is 1 upon n and 1 upon n and 1 upon n and 1 upon n, we essentially get small n upon capital N. We call it favorable upon total thing. So this is the place from where that favorable upon total formula is arises. Now, let's move on to the next thing that we did in probability 1.0. And the next thing was addition law of probability. Addition law of probability is mostly used when you have more than one intersecting event in a given sample space. For example, in a class, few like physics, few like maths, but few may be there who have both physics and maths as their liking. For example, in a society, few have cat as pet, few have dog as pet. Few families might be having both cat and dog as a pet. We don't have multiple random experiments here. We don't have multiple sample spaces here. We have just one random experiment and one sample space, one society, multiple families, and we have one random experiment identifying the family, whether that family has a pet or not. But so there is just one sample space. We don't have any compound random experiment. We don't have any compound sample space. There is one sample space only, but there is one event having dog aspect, and there is another event having cat aspect. There is one event having mathematics as the favorite subject. There is another event having physics as the favorite subject. And then there are people who have both mathematics and physics as their favorite. People having cat as pet, people having dog as pet, and then there are people who have both cat and dog as pet. So there is always some intersecting space between two events defined on the same sample space. No. Actually, there can be three events. Like if you remember, we have solved a problem like this. One given sample space, and we defined three events. You remember that party problem? Few people wearing a red shirt, few persons wearing a black shirt, and few of them are having yellow shoes or green shoes. Okay, so we can have some intersecting area between these events defined on the same sample space, and then we write P A union B using inclusion exclusion principle. We write P A union B is equal to PA plus PB minus PA intersection B. I hope you are okay with me recapitulating everything because we have had 3 days gap. And then similarly, if you want to write probability of A union B union C, then you are going to write PA plus PB plus PC, PA plus PB plus PC minus P intersection A intersection B minus probability of B intersection C minus probability of C intersection A. And finally, one last term, and that last term is adding the probability of common area between all three events. Perfect. So these two are additional law of probabilities. If you remember, we have used it multiple times. For example, probability of bad weather or no bad weather, wala problem. So when you're writing probability of no bad weather, probability of no bad weather, are you going to directly use additional law of probability, or are you going to use some other law and then additional law of probability? Somebody come forward and tell me.
De Morgan's law used first, sir.
De Morgan's law. Wow, lovely. De Morgan's law. So when you say no bad weather, you are basically saying no rain and also at the same time no storm. Whenever you get a problem, neither of these in one given sample space, it is a standard template and it is a very popular probability problem. It is a standard template and a very popular probability problem. Whenever you get one such scenario, one such problem where they say neither of this and nor that, neither this nor that, neither rain nor storm, no bad weather. I don't want any bad weather anymore. Okay. So in that case, you first use De Morgan's law, that this is intersection, and then it becomes probability of complement of unions, and probability of complement of unions can be written as probability of R. Sorry, it can be written as, first of all, 1 minus probability of complement removed from here now. And then you can apply additional law of probability. Then you can apply additional law of probability. Make sure that you have completed the DPPs, because DPPs, after solving DPPs only, you will be getting a command over probability. First step is, of course, having a systematic structure of learning. Unfortunately, I'm not criticizing anyone, but this is an unfortunate thing that the theory of probabilities in 95% resources. Theory of probability is very, just like probability is about random experiments. So theory of probability is also very randomly presented. You won't be able to make a systematic, identification that when should I apply what principle, and how those principles have been evolved. So I have tried my level best. I have tried doing the justice with such a beautiful branch of mathematics, with such a fascinating branch of mathematics, which actually started with gamblers, probably the only field of science that did not start with scientists, but with people who nobody considers worthy. But look, this is certainly not only a fascinating branch of mathematics, but also today, every single manufacturing design, every single engineering design, to every single supply chain management that's being done, it's being done not without probability theories. I gave you so many examples in the beginning of the course. Coming back to the topic, we then entered into probability 2.0. What is probability 2.0? Probability 2.0 is, we then entered into the probability 2.0, and probability 2.0, we covered, first of all, compound random experiments. Compound random experiments, you tell me, if one random experiment having sample space of capital N1 number of elements, capital N1 number of equally likely outcomes. And another random experiment has a sample space of capital N2 number of equally likely outcomes. So compound random experiment is what? That now you are simultaneously dealing with two sample spaces. Now you are simultaneously dealing with two sample spaces. That roll a die and then roll a die. Toss a coin and then toss a coin. Roll a die and roll a die. Toss a coin and toss a coin. Draw a card and draw a card. Okay. So there are multiple sample spaces present. In fact, there could be even more. So this is one sample space having capital N1 number of equally likely outcomes. This is another sample space having capital N2 number of equally likely outcomes. This is another sample space having capital N3 number of equally likely outcomes. Then you tell me, if I define a compound random experiment, if I define a compound random experiment involving all these random experiments, then the overall sample space will have how many equally likely outcomes?
Sir,
As
N1 into N2 into N3, sir.
N1 into N2 into N3 into N4. Exactly. So S has N number of equally likely outcomes, N number of equally likely outcomes where N becomes N1 into N2 into N3 into so on and so forth, Nk. All right, then we move on to the next thing. That suppose now you are defining an event that what is the probability that you are getting? What is the probability that you are getting 2 in first roll of die, and you are getting 4 in the second roll of die, and you are getting 1 in the third roll of die and 5 in the fourth roll of die? Or what is the probability that you are getting an even number in the roll of die, and you are getting a red card when you are drawing a card from the pack, and you are getting a head when you are tossing a coin also, and you are observing the person spending more than 10 minutes in an ATM machine? A compound random experiment, at least in your mind, can be created by combining any two similar or dissimilar random experiments. For example, stand outside the ATM machine and toss a coin. What is the probability that stand outside an ATM booth and toss a coin? What is the probability that your coin is going to turn head and the person who entered into the ATM machine will spend more than 10 minutes? So how do you calculate it? By defining one global event that gets satisfied when first sample space A1 event happens, second sample space A2 event happens, third sample space A3 event happens, kth sample space and AK event happens. So if you define an event in the global sample space, in the overall sample space, if you define one event in the overall sample space, and compound random experiment, I told you, can be conceptualized by combining either similar random experiments or even dissimilar random experiments. Today, the election results are being announced. And I'm rolling a die. So what is the probability that die will turn 6 and one particular party, let's say party XYZ, will win the mandate of the people? That is again a compound random experiment. That's again a compound random experiment. Cool. One random experiment, how many runs? Shikhar Dhawan is going to score today. Another random experiment, whether India will win or not. Now, you make a compound random experiment, Shikhar Dhawan will score, though they are not independent events actually. They are dependent events. Why? Because if Shikhar Dhawan will score a century, then winning chances of India will become greater. So they are not two separate sample spaces. As of now, we are discussing only separate sample spaces. As of now, we are discussing only those sample spaces such that outcome of one event or outcome of one random experiment doesn't affect the outcome of second random experiment. For example, what is the probability that the power will be gone in the next half an hour at my home? And what is the probability that US stock market will open below the level of where it closed yesterday? Now, these two events are not even in the remotest thought, they are not affecting each other. What is the probability that in next half an hour, power will be gone in my home? There'll be no power supply, and US stock market will open in red today, open below the level where it closed yesterday. These two events are not connected, but we are still combining it. That's how a compound random experiment comes into the picture. And an event gets satisfied by satisfying A1 from one sample space and A2 from another sample space and A3 from another sample space and A4 from another sample space and AK from another sample space. So in that case, the probability of that global event will be simply the product of probability of all these events. Then we tried solving some problems based on combined application of we started solving some problems based on combined application of addition law and multiplication law of probability. This is multiplication law, this lower one. So then we used combined application of addition law of probability and multiplication law of probability. Let's create the short forms. Addition law of probability is ALOP and multiplication law of probability is MILOP. Multiplication law of probability is MILOP. ALOP, MILOP. So combined application of ALOP and MILOP. All right. And how do we do that combined application? Combined application is simple, that you break an event into multiple OR, comma, multiple AND combinations. Multiple OR, comma, multiple AND combinations. For example, if you are rolling 2 die, what is the probability of getting at least, if you're rolling 2 die, what is the probability of getting at least 2 on at least 1 die? What is the probability of getting 2 on at least 1 die if two dice are rolled? So how do you calculate it? You first break it into combined application of addition law and multiplication law. How do you do that? That one thing is that you first time get 2, but second time you don't get 2. But there is one more way in which your event can be satisfied. And that way is that first time you don't get 2, and the second time you get a 2. And the second time you get a 2. But there is one more way, because it says at least. That means you are satisfied even if you get both twos. One die, second die, both you roll, and both of them are appearing, both of them are turning the top face as 2, the digit 2, number 2. So there is one more way in which your event can be satisfied, that I get a 2 and again I get a 2. I get a 2 and again I get a 2. Wow. So now you are going to use addition law also, and you are going to use multiplication law also. Every OR will use addition law, and every AND will use multiplication law. So now you are going to say probability of getting 2 and probability of not getting 2 plus probability of getting 2, not getting 2 in the first die, but probability of getting 2 in the second die, or probability of getting 2 in the first die also, and probability of getting 2 in the second die also. So we are going to get 1 upon 6 into 5 upon 6, 5 upon 36, and then we are going to get 5 upon 36, and then we are going to get 1 upon 6 into 1 upon 6. That becomes 1 upon 36. Finally, we get 11 upon 36 as the final answer. Like this, we can actually formulate so many problems on the combined application of addition law of probability and multiplication law of probability. This is the beautiful summary of everything that we have done so far in probability so far. This is everything that we have done so far in probability. All right, now we go ahead and complete our next step before we can start the last leg of probability 3.0. So before starting the last phase, the last episode of probability, which is probability 3.0, let's first go ahead and complete one last remaining task. And that last remaining task is that, you see, if you are rolling only 2 die, then writing this, first you are getting 2, second you are not getting 2. First you are not getting 2, second you are getting 2. And first you are getting 2, second you are not, second also you are getting 2. Writing this manually is still manageable. You can write this manually. There are 3 possibilities only. But when this number of times you are rolling the die grows bigger, when this number of people you are asking that buy my product, buy my product, buy my product, buy my product, when that number grows bigger, it becomes unmanageable. I have one particular brand. Let's say I have let's say some pen to be sold, and I have multiple units, by the way, and I'm going to target some 20 potential customers today. So I target those 20 potential customers that, look, this pen is something magical. Using this pen only, I topped IIT Kharagpur campus. So buy this pen and you are also going to top in your respective school or respective college. Cool. So when I'm going to say target this to 20 customers, what is the probability that 3 of them will buy the pen? And suppose I know the probability of each person agreeing to buy my product. Now, this becomes unmanageable. This becomes totally unmanageable. Let me save this and let us try getting our hands on this problem, that I'm going to target 20 potential customers to buy a pen. And my dear friends, I'm going to target 20 potential customers to buy a pen. And my dear friends, I know each individual having a probability of only 0.12, only 12% to buy the product. What is the probability that out of 20 customers, 20 potential customers, 3 will buy the product? Now, let's give a score to this problem. Can you please tell me what's the score so far?
$18, sir.
So as an 18th problem, probability that a person would buy my pen is 12% only. Probability that a person would buy my pen is 12% only. Wow. Feeling so, I especially feel so relieved after sneezing. God bless me. So a person would buy my pen that has probability of 12%. Cool. Now, I'm going to target, or I'm going to, let's say, ask 20 persons. I approach 20 persons or 20 people with a pitch to buy the pen. With a pitch to buy the pen, I approach 20 such potential customers. With a pitch to buy the pen, I approach 20 persons. Now, what is the probability that exactly 3 of them will buy? And this is going to be frustratingly monotonous and cumbersome problem if you actually approach by manually counting. Manual counting becomes so frustratingly boring. So what is the probability of exactly 3 of them buying the pen? And if you think exactly 3 of them buying the pen, and if you think the answer is 0.12 into 0.12 into 0.12, you are absolutely wrong. If you think that the answer is going to be that first person, the answer is going to be 3 people buy and remaining 17 don't buy. And if you think that we are going to answer this question like, because 3 people buy, so 0.12 and 0.12 and 0.12, and because other 17 people don't buy, so 0.88 into 0.88 into 0.88 into 0.88 17 times. No, this is not the correct answer. This answer is still wrong. Can somebody come forward and tell me why this answer is wrong? A person would buy my pen. Individual probability of one person buying my pen is 12%. Now, I approach 20 potential customers with a pitch to buy the pen, that do buy this pen. This pen is, magical, and I have done wonders using this pen. I'm just kidding. So exactly 3 of them buying the pen. What's the probability? And this answer is wrong, by the way. This answer is wrong. Now, as I said, if you are going to list all the possibilities manually, it's going to be one hell of a job. Why? Because you are going to say first person, second person. Actually, we should add and also first person agrees to buy the pen. Second person also buys the pen. Third person also buys the pen, but fourth person don't buy. Fifth person doesn't buy. Sixth person doesn't buy. And then 17th person also doesn't buy. 17th person also doesn't buy. This is one way to satisfy my requirement. This is one way to satisfy the requirement given. But there is one more way, mutually exclusive way. There is one more mutually exclusive way. And that mutually exclusive way is the first person agrees to buy the pen, and then second person agrees to buy the pen, but then third person doesn't agree to buy the pen, and fourth person agrees to buy the pen. Sorry, third person doesn't agree to buy the pen, but fourth person agrees to buy the pen, and then fifth doesn't agree, sixth doesn't agree, and finally 17th also doesn't agree. There can be some beautiful problems created on combined application of law of addition, addition law of probability, and multiplication law of probability. I don't know about you, but I always, whenever I study or teach probability, I always feel another level of joy. This is such a fascinating branch of science that we know this is that branch of science that accepts our limitations. And when humans, there are rare occasions when humans accept their limitations. Probability is one such branch. We accept our limitation that yes, we know things are uncertain, but we will at least predict a chance of occurring 90%, 80%, 70%, 75%. We know that things are uncertain, but we will quantify that uncertainty. We'll quantify that randomness. We'll give it a value that how uncertain it is. We accept our limits that we humans are not having that capability of knowing with certainty if something will happen or not. So anyways, you notice this problem is again a beautiful problem where you can keep listing such things. And there are actually 2 pages will be full. Actually, more than 2 pages will be full. If I simply keep writing this kind of thing, and then this kind of thing, and then this kind of thing, actually 2-3 pages will go full. After that, only it might be possible to list all such possibilities. People said that one thing is common between them. And what is that one thing that is common between them? That every time I have 0.12, 0.12, 0.12, and then I have 0.88, 0.88 power 17. And last term, I should actually write 20. Because I'm asking 20 people now. So there is one thing common between all these mutually exclusive ways of fulfilling the given requirement. 3 buy and 17 don't buy. Fulfilling this requirement has multiple possible ways, and they have one common thing, that every single time I have 0.12 and 0.12 and 0.12 and 0.12. Every time I have 0.12, 0.12 and 0.12. And then 17 times we have 0.88, 0.88, 0.88, 0.88, 0.88, 0.88, 0.88, 17 times. Is that clear? So one thing is common, and that is that I have to write 0.12 power 3, and I have to write 0.88 power 0.88 power 17. If somebody can only tell me that how many times, I'm repeating this, number of ways in which 3 places can be filled out of 20 places. Number of ways in which 3 glass out of 20 glasses can be filled with water. Number of ways in which 3 spots out of 20 spots can be filled with a tag. Number of ways in which 3 spots out of 20 spots I can sit on a platform. Number of ways in which 3 places, number of ways in which 3 places can be selected. Mind it, I'm just selecting the places. Number of ways in which three places can be selected out of 20 places. And that we already know. Previous class, we found a scientific way of doing this, that how to select 3 places out of 20 places, how to select 3 objects out of 20 objects, how to select 3 things out of 20 things, how to fill 3 glasses out of 20 glasses. So there are 23 ways to do this, because if I'm going to do by manually counting, it will become a nightmare. Believe me, guys, it will become a nightmare. So now you ask your calculator that, dear calculator, do tell me what's this value, 20C3. Dear calculator, tell me what is this value, 20C3. 20C3 multiplied by 0.12 power 3 multiplied by 0.88 power 17. This is 0.2242%. It's still not a big probability, given that the probability of one individual buying my pen is still very small. Just 12 out of 100. Just 12 out of 100 is not a very good chance, but still, if I ask 20 people, I have maximized chances of selling not just one pen, but more than one pens. And that's going to be 22.421%. That's going to be 421%. Lovely. So this is something that we know now. Now I take you to the next probability 3.0. So let us go ahead. And start probability 3.0. In probability 3.0, the first thing that we are going to do is to build some prerequisite, and then we will move on to the main topic. The main topic is a bigger one and is again a very amazing topic, you can say. But before we can go into that amazing topic, we have a prerequisite to be fulfilled. We have a prerequisite to be fulfilled. So let's have a look at that prerequisite. And by the way, we will try doing that prerequisite through some problems. So as a 19 problem, let's say I want to find out the probability of getting a 1 in rolling a die. When you're rolling a die, I want to calculate what's going to be the probability of getting 1 when you are rolling a die. And you are going to say that this is an easy problem. Getting a one in rolling a die is simply 1 is favorable, and total number of 1 is favorable, and total number of elements in whole sample space 1, 2, 3, 4, 5, 6. So 1 is favorable and total number is 6. It becomes 1 upon 6. So basically you have a sample space of 6 number of elements. This is the whole sample space of 6 number of elements, and I just wanted to get 1. That's it. Let's say 1 is an event. Getting 1 individually, getting 1 is an event. Now suppose somehow somebody told me, and somehow I know, or die has been rolled, but it is hidden from me. Die has been rolled and it is hidden from me. And now somebody is saying that what is the chance that it already came 1? Then I say, give me some hint. Give me some hint. So that person is like, okay, I'm giving you a hint that the die has turned up an odd number. Now tell me, what is the chance that a 1 appeared? Now my information has been updated. Probably the other guy did not know that this guy knows probability and he's going to use that information. So I simply told him that it's an odd number. Can you now tell what's the chances of getting a 1? Earlier, based on very random events, my information was that getting a chance of getting a 1 is 16.67% only. But now suppose someone rolled the die hidden from me, and then he sees and he says that what's the chance that die got 1? And I'm like, give me a hint, man. Okay, here you go. It's an odd number. It's an odd number is now my updated information. Let's say let's say somebody told me that it's an odd number. Somebody told me that it's an odd number. It's an odd number. Somebody told me. Now, what is the probability of getting 1, given that it is known that it's an odd number? Now you know your favorable part of sample space is having only 1 element, and now you are not going to search in whole sample space. Now you are going to say that I already know it's an odd number. So I'm trying to get 1 out of 3 number of elements only. I'm trying to get a 1 out of 3 elements only. So given that it's an odd number, probability of finding a 1, I'm going to define that probability as 1 upon 3. I'm going to define that probability as 1 upon 3. My dear friends, बहुत ध्यान से समझिए. This is something, if you will understand, then only you will understand the main topic. If you don't understand this, then you are not going to understand the main topic. So 1 upon 3 becomes the probability. Getting a 1 can be defined as event A, and we already know that it's an odd number, can be defined as event B. Sometimes in a sample space, we know that something has happened, and then we want to know that what is the probability that this will also happen. We know that rain is already happening. Now tell me what is the probability that storm is also coming. We know that this this student has already scored 600 marks out of 1000 marks. You tell me now that he scored 60% in mathematics. We know that India has won already, or Kohli has scored a century already. Now tell me, given that Kohli has scored a century, tell me whether India won today or not. And suppose you did not see any news, you did not follow the game. Tell me whether India won today or not. You'll say 50-50%. But the moment I say that Kohli scored century today, now you tell me whether India won today or not. Then you'll say, okay, Kohli scored century today. 70% chances are India won. Or 80% chances are India won. Why? Because from past historical data, your information is updated now. You say, okay, Kohli scored century. Given that Kohli scored century, I need to determine the probability of India wins the match. This will be a different estimation. But if I ask you that what is the probability that India wins the match, given that, what is the probability that India wins the match, given that India wins the match, given that Kohli scored a century? So if I know that Kohli made a century, and then I want to know what are the chances that India wins, then I know that it will have a different estimation. This, my dear friends, is known by the name. This, my dear friends, is known by the name conditional probability. If somebody asks me what are the chances of India winning the match today, I'll say 50%. If somebody asks me what are the chances that India is winning the match, given that Kohli has already scored century, then probably my answer is going to be that India winning the match is 80%, even though same cannot be applied for RCB, no? Kohli made century. Because RCB loses the match, that probability is always higher, irrespective of the probability of given event. Huh? No, I'm just kidding. I also wish RCB to win the IPL at least once. So A given B, this is called conditional probability. We call it, in the language of probability, we call it conditional probability of A given B. So it's an odd number. Now, I don't want to define things like this. I still want to follow the whole sample space. You see, both the events, probability of getting one and the event of getting an odd number, both the events, they are not sample spaces now. They are not really, neither of them is a sample space, both are events actually. So I just want everything to be defined on the original sample space, on the initial sample space. And that's why I introduce that 1, 2, 3, 4, 5, 6 in numerator also, that 1, 2, 3, 4, 5, 6 in numerator also, and I introduce 1, 2, 3, 4, 5, 6 in denominator also. So let us introduce 1, 2, 3, 4, 5, 6 in denominator also. Why I'm introducing this? Because I know that my initial probability has been defined by n upon capital N. That's why I'm forcefully introducing capital N here. So this is actually number of elements that satisfy the event A. And now I have in denominator total sample space, total number of outcomes, and 135 is actually representing the favorable outcomes. 135 is actually representing the favorable outcomes that satisfy event B. So this is something that is satisfied by event B. Sorry, event B upon capital N. Actually, frankly speaking, numerator we have that one common with B. That one is the common element with event B. Otherwise, if I say, given that it's an even number, now you tell me what is the probability of one. Then one has favorable as 0. If I say it's an even number, now you tell me what is the probability of getting 1. Then there is no favorable element available anymore because it's an even number already. And if somebody gives me this kind of hint, I will give certain estimation. No uncertain, no random thing. Then okay, give me the hint. No hint. Tell me what is the probability, what is the chance of 1 on dice? No, please give me the hint. Please, please give me the hint. Okay, I'm giving you the hint. It's an even number. This is not a hint. This is an answer actually. The moment you say it's an even number, it can't be 1. So with an even number, there is no intersection of my events. So notice that in the numerator, it's actually the number of elements that have intersection with the bottom event. We get probability of A given B is equal to, this is now the definition of probability of commonly satisfying A and B, and in the denominator I have probability of, B getting satisfied. If you already understood, I request you to mug this up. If you did not understand, not a problem. We will anyway take one more to enhance your understanding, to increase your understanding. And this time I'm going to take, okay, let's save this first. And this time I'm going to take as a 20th problem. Let's say there is a box. And that box contains 4 white marbles. And that box also contains number of red marbles. And the box also contains number of green marbles. So there are a number of green marbles contained in that box. Okay. And somebody is going to ask me that if I have drawn a marble randomly, if I have drawn a marble out of that box randomly, what is the chance that I got a green marble? If marble has been drawn randomly from the box. If a marble has been drawn randomly from the box, then what's the chance of it's being green? And this is such a straightforward application of the very first type of problem we solved, finite sample spaces with equally likely outcomes. And we are not even asking for any compound experiment or addition law of probability or anything like that. No. So just probability of getting a green marble. Probability of getting a green marble is very simple here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 marbles are green, and that's favorable thing for me. 9 marbles are green, and that's favorable thing for me. And my dear friends, out of the, apart from those 9, I have 1, 2, 3, 4, 13, and then 14, 15, 16, 17, 18, 19, 20, 21. Out of 21 total number of marbles, 9 of them are green. So there are 9 upon 21 chances of getting a green marble in whole sample space. I have very clearly written, if getting a green marble is defined as event A, if I define event A as getting a green marble, then number of favorable things to that event is 9. And then there is capital N. What is capital N? Capital N is overall sample space. Perfect. 9 upon 21. But now suppose somebody has drawn one marble randomly, and then he told me that, tell me, he asked me that what's the probability? That box is there, and I'm going to draw a marble randomly, but I'm not going to reveal that marble. And then I ask you that what's the probability that this marble is green? Then you got a hint again. That give me some hints. Okay. What is the probability that this marble is green given that it's a colored one? Given that it's a colored one, immediately increases your certainness. Your uncertainty gets reduced. Now your certainty has increased. Now you know that I definitely know that these 4 candidates are no more having any scope of including in the picture. They have not become a reality. I know that. So suppose somehow there is a hint given that what is the probability of getting a green marble given that we got a colored one in the draw. Given that we got a colored one in the draw. We got a colored one in the draw. Cool. What is the probability of getting a green marble? My dear friends, probability of getting a green marble, given that you got a colored one. So let's define one more event now. And that event is getting a colored one. That event we are defining getting a colored one. So now again you have 9 favorable, but in how many? Now no more 21, but 17 only. 1, 2, 3, 4, 5, 6, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So out of 17 only you are searching. That out of 17 colored marbles, 9 are green. And if 9 are green out of 17 colored marbles, now my probability is going to be 9 upon 17, where 9 represents the number of common elements present in green and colored events. And my dear friends, the 17 represents total number of elements satisfying the colored marble event. 9 is satisfying. 9 is satisfying the number of elements that are also a green marble and also a colored marble. And 17 is satisfying the whole space of colored marbles. But since people said now we have another way of defining a probability that's not good, let's keep our way of defining probability as a standard thing favorable upon total sample space only. So that's why we are introducing 21 in numerator also, and we introduce 21 in denominator also. And now this represents number of elements present in intersection of events A and B divided by capital N, and this represents number of elements present in the number of elements present in the colored event divided by capital N. My dear friends, this is very clearly the definition of PA intersection B, and the denominator one is very clearly the definition of probability of B. So probability of A given B has already happened is going to be written like this. Probability of A given that B has already happened is equal to probability of A and B getting satisfied simultaneously divided by probability of B alone. Now I can write probability of A intersection B. Probability of A intersection B is equal to probability of B multiplied by conditional probability of A given B already happened. I remembered this formula in a way that this is like the symbol of division, and this is, then there is multiplication, and if there is same thing in multiplication and then there is same thing in division, that thing gets cancelled. So that thing should be visible getting cancelled. Always remember this, that you can never write it like PA into PA oblique B, no, because now this thing is not visible getting cancelled. So you should remember it that way, that in this formula of conditional probability, that multiplication and division thing always look to be getting cancelled, must always look to be getting cancelled with each other. So that division thing and multiplication thing must always look to be getting cancelled with each other. My dear friends, this is called conditional probability, the prerequisite of understanding the main topic of probability 3.0. But the main topic of probability 3.0 will be, we have time. So I thought that maybe we are approaching the start time of the second class. So this is called conditional probability. I hope you now understand the essence of conditional probability, the essence, the theme, the very crux of conditional probability is that in one given sample space, your information gets updated. And once your information gets updated, probability of green is something else. But probability of green, given that we have already got a colored one in draw, is a separate number. It's not the same number anymore. You cannot write 9 upon 21 anymore. And since defining probability with respect to total sample space is always going to be a better idea, that's why we introduced capital N in numerator and capital N also in denominator. That's why we introduced capital N in numerator, and that's why we introduced capital N also in denominator, so that we can again write them in the way our usual definition of probability works. Our usual definition of probability works. Okay? Okay. So let's go ahead. You can keep solving multiple problems, but you now understand the essence. My dear friends, just to be satisfied, let's solve one more. So the previous one was 20 or what? Yes, 20. Let's move to 21st problem. In a production run, 20% of screws are imperfect, out of which 72% are oversized, and 72% are oversized, and 26% are 28%, sorry, 72 plus 28 becomes 100. 28% are undersized. Now there is a lot of 40 screws, and one screw is randomly picked for quality inspection. What is the probability that the screw is undersized? What is the probability that the screw is undersized? So out of 40 screws, and let's keep it. Let's keep it. Let me just check. I should get a decimal. I'm obviously not going to get any decimal with these numbers. So let's take this as 70 and let's take this as 30. And let's take the lot of 50 screws. Okay, so 20% of the screws in a production run are imperfect, out of which 70% are oversized and 30% are undersized. Now, in a lot of 50 screws, one screw is randomly picked. One screw, just one. So one screw is randomly picked. I'm going to pick one random screw. Now, what is the chance that the screw is undersized? You are certainly going to solve it, just like probability 1.0, that there are, in the total sample space, there are 50 screws present. Out of these 50 screws, out of these 50 screws, number of defective screws, how many? Number of defective screws are 50 multiplied by 0.2, and 50 multiplied by 0.2 becomes 10. So there are 40 perfect screws, and there are 40 perfect screws. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. There are total 40 perfect screws and 10 defective or imperfect screws are present. Let's represent imperfect screws as by colored pen, and out of 10, 7 are naturally going to be, if there are total 10, out of them 7 are oversized, and 3 are undersized. So let's represent 1, 2, 3, 4, 5, 6, 7 oversized, and then there are 3 screws undersized. Now, what is the probability that a given screw is undersized? That's such an easy job. There are only 3 things that favor you out of 50 things. There are 3 things that favor you out of 50 things. So 3 divided by 50, this becomes 0.06. Or in terms of percentage, you can say 6%. Probability that a screw is undersized. But now suppose that somebody told me that I selected a screw randomly from a lot of 50 screws, and then somebody told me that selecting a screw, given that selecting an undersized screw, given that the selected screw or the picked screw or the drawn screw, selected screw is defective. The moment this given information is updated, that what is the chance of getting an undersized, screw, given that the selected screw is defective. Now my space has been updated. I don't have to search in whole sample space anymore. This is the sample space of undersized screws, and this is the sample space of all defective screws. This is the sample space of all defective screws. My dear friends, now it has been given that what is the probability that we are in this green thing, given that we already know that we have entered into the yellow thing. Given that we are already into the yellow thing, what is the probability that we are in the green thing? Given that we are already in that yellow space, what is the probability that we are in the green space? Now, this is what you call conditional probability. And you can directly, actually, for conditional probability, you don't need that formula. You see, every time we are solving the problem and then we are converting it into the formula. We are not using the formula. We are, in fact, solving the problem, and last, we are ending the problem with saying, ki, oh, this is transforming into this formula. We are never, ever, never, ever, never, ever solving. We are never, ever, never, ever, never, ever using the formula to solve the problem. We are simply solving the problem just by manually seeing whole situation. So if we manually see the whole situation, there are 3 favorable events out of 3 plus 7, total 10 defective screws. Because now I know that why I'm going to divide by whole sample space if I know that I'm in that yellow box. If I know that I'm already in that yellow circle, then I'm naturally going to say keep only 10 out of, I know that on any one of that, those 10 screws have already been selected. But since the definition of probability has been created basis whole sample space, people said it would be better if we don't create again a new definition of probability, but rather try manipulating this so that it fits into the old definition. My dear friends, 3 represents the number of elements satisfying me, number of elements satisfying the common area between green and yellow, and 10 represents the number of elements in the yellow area. People said it would be better if we keep using the same definition of probability. So divide by 50 in numerator also, and divide by 50 in denominator also. And I'm going to then able to write the numerator representing probability A intersection B and the denominator representing probability B. My dear friends, this becomes the final one time more the definition of conditional probability. Conditional probability is A intersection B upon probability of B. But we are not going to memorize this formula in this current format. We are going to memorize this formula in a different format. And that is A intersection B is equal to PB multiplied by PA given B. PA given, that vertical line is read as given. PA given B. Given B. That vertical line, we read it as given. Okay, so B and B are going to get cancelled. That is one way to memorize this. This was just a prerequisite to build something bigger and finally close the chapter called probability today. In the next class, we are going to understand the law of total probability, and also one of the most powerful and one of the most used and abused principle of probability called Bayes' theorem. So Bayesian probability and Bayesian statistics today is the backbone of so many fields of economy and science and technology. And we'll get a glimpse of it little bit, that what Bayesian theorem is, but in the next class. In the next class, we come across the law of total probability, and we also understand the Bayesian theorem. If you guys want to ask something, you can go ahead and ask.
Sir,
Hmm.
in the 18th problem, how we can treat it as that given problem as arrangement or selection?
It will be visible from the problem itself. In probability, arrangement will rarely come. It's like 99% cases, it's going to be selection only. Because you need to select spots that every time you just need to select spots. For example, suppose I want to calculate probability of getting 2 heads out of 7 tosses. Which means what? I want to get head, head, and then tail, 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 tail. Or I want to get head, head, and tail, 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 tail. Or I want to get head, head, and tail, 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 tail. Or I want to get head, head, and tail, 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 tail. Or I want to get head, head, and tail, 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 tail. Or I want to get head, head, and then tail, 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 tail. All right. These are the 1, 2, 3, 4, 5, 6 ways of getting ahead by keeping first one fixed at head. Similarly, we can do this by keeping the second one fixed at head. Once again, we can repeat with third place fixed at head. But though don't make it 6 multiplied by 7. No, it's still a selection. Why? Because you need to select 2 places where head can be put. You just need to select 2 places where a head can be put. So selecting first place and third place is actually the same thing as selecting the third place and the first place. The sequence doesn't matter. The order doesn't matter. When sequence doesn't matter, then distinct selection is only one. You might be representing it 2 times. It will become arrangement, but arrangement doesn't matter here because first coin and third coin getting head is same thing as third coin and first coin getting head. First coin and fourth coin getting head is the same thing as fourth coin and first coin getting head. So basically, we just want to select 2 places out of 7 places. We don't want to select 2 heads. No, don't confuse it by applying permutation combination on head and tail. We are not really applying permutation combination on coins. We are applying permutation combination on places that I have to place 2 heads out of 7 places. How to identify those 2 places? Mind it, identifying 5th and 7th place is the same thing as identifying 7th and 5th place. Identifying first and third place is the same thing as identifying third and first place. So I just want to select, not arrange. Because if I'm going to say 1, 3, and 3, 1 out of 7, I have to make an arrangement of 2 numbers. Then these 2 arrangements are different, but they represent the same selection. So in probability problems, 99% of the times, we just need to make a selection. That's it.
Okay, sir.
Hmm. All right, let me just see, is there anything someone asks? Arey bhai, why this YouTube is opening at shorts only? I'm not interested in shorts. So let me open Telegram. Oh. Good afternoon, Mithun. Good afternoon, Ariz. आपका ऑफलाइन क्लासेस कब से स्टार्ट होगा? ऑफलाइन क्लासेस का तो एक बार आप डिजाइन पोर्शन कंप्लीट कराएंगे परमार जी। बेटा अभी तो मैं कुछ ऐसा बता नहीं सकता कि मैं क्या कंप्लीट करवाऊंगा यूट्यूब पर। बैचेस के लिए तो आई हैव हैव टेकन द फीस, सो वो तो भाई मजबूरी है मेरी। मजबूरी नहीं है, मतलब कर्तव्य है, बट अगेन यूट्यूब का तो अभी से कुछ नहीं बता सकता मैं। आपका ऑफलाइन क्लासेस कब से स्टार्ट होगा? ऑफलाइन क्लासेस में जरा फिजिबिलिटी थोड़ी इंक्रीज होनी चाहिए। अभी तक ऑफलाइन क्लासेस में कुछ मुझे ऐसा फिजिबिलिटी दिखा नहीं है, तो अभी तक के रिस्पांस के हिसाब से तो आई डोंट थिंक दैट इट्स गोइंग टू बी फिजिबल। सो एक बार मैं फिर से फॉर्म फ्लोट कर दूंगा, अगर मैं देखता हूं, मुझे कोई प्रॉब्लम नहीं है, बट देयर शुड बी सम स्टूडेंट्स हु आर इंटरेस्टेड। द नंबर दैट आई एम हैविंग इन माइंड इज 30, कि अगर 30 स्टूडेंट्स इंटरेस्टेड हैं तो हम 30 लोग मिलकर इतिहास क्रिएट कर सकते हैं। ऑफ कोर्स 30 आप और एक मैं। मैं एक बार फिर से ग्रुप में, टेलीग्राम ग्रुप में फॉर्म फ्लोट कर दूंगा और वहां जो लोग इंटरेस्टेड हैं फॉर्म भर सकते हैं। ऑल राइट पीपल, थैंक यू सो वेरी मच, बाय बाय। नेक्स्ट क्लास स्टार्ट होगी 4:45 को, और प्रोबेबिलिटी की नेक्स्ट क्लास काफी इंपॉर्टेंट है। हम लोग करने वाले हैं लॉ ऑफ टोटल प्रोबेबिलिटी एंड बेसियन थ्योरम। वी आर गोइंग टू डू लॉ ऑफ टोटल प्रोबेबिलिटी एंड बेसियन थ्योरम।